Hi everyone, welcome back to Science Sketchbook. In this video, I will be covering the difference between constitutional and stereo isomers. Looks like we're starting with a quick bark reminder from Sketch. So, the background and review knowledge you will need for this video is being able to interpret bond line structure. This is where molecules are drawn out in a simplified stick format. If you're unsure, feel free to check out my video on that topic. Okay, quick overview. What is an isomer? These are molecules with the same molecular formula, or same number of the same atoms, but a different arrangement of those atoms. By arrangement, that can mean a different structure or a different spatial layout. That's the main idea between the two isomers we're covering. Structurally different molecules are constitutional isomers, and spatially different isomers are stereoisomers. Let me show you what I mean. So, for the structural difference, I want you to think constitutional connectivity. Once again, same molecular formula, but they are connected in a different order. Sketch the Dog is here to illustrate that for you. So, let's say the formula for a dog is 4 legs, 2 ears, 1 tail. Its kind of molecular formula can be seen as legs, 4 ears, 2 tail, for example. Again, the molecular formula just shows the types of atoms present and the number of each, not the exact connectivity. So here he is. Connection-wise, he has a tail at the back end, 4 legs in order, and a couple of ears on his head. But what if we changed the connectivity? In this form or isomer, he's connected in this order here, what you expect of a normal dog. But let's say we connect things in a different order. In this form or isomer, his leg and tail are connected in a different order now. At this time, you've got 3 legs at the back end and the tail is kind of in the middle, right? He still has the same number of legs and tail and such, so his formula didn't change, but he is certainly structurally different, isn't he? Thus, those two forms, whether he likes them or not, are constitutional isomers. So, got that? Constitutional connectivity. Let's try it with an actual molecule. Let's say we have a molecule with 5 carbons and 12 hydrogens. Its molecular formula will be C5H12. So, start by drawing an arrangement of 5 carbons and test out if all the atoms are there. So, let's try this one. If I show in all the implied hydrogens, go ahead and count them up. Is this 5 carbons and 12 hydrogens? Yeah, it adds up. Now, to find a constitutional isomer, just disconnect 1 carbon and attach it somewhere else, just like we did with Sketch's leg and tail. So, how about this one? It is indeed 5 carbons, it just has 1 branching off the second carbon instead of all in a line. And to confirm, if you count those up, it does indeed have its 12 hydrogens. So this is a constitutional isomer of that first one. If we connect it a different way, we can branch them all off of 1 carbon. Again, still 5 carbons. And, yep, 3, 6, 9, 12 hydrogens there. All of them have the same molecular formula, different connectivity, so they are indeed constitutional isomers. You can try disconnecting and reconnecting some more, but these are the only unique ones, by the way. If something is equal by rotation, it doesn't count as an extra isomer here. See in this little cloud over here, no matter how I spin that molecule, you could have drawn it any which way, but it doesn't make it a new constitutional isomer. It's still equal to that second isomer we drew. Now, before we continue, one last reminder for you. Again, I am emphasizing that isomers need to have the same molecular formula. That's the one that just purely shows the type of atoms and the number of them, no matter where they are in the molecule. The condensed formulas will look different though, as they show the actual structural differences written out. They will still have the same number of the same atoms, but they can look very different. Take a look at these. When they're all in a line, it's CH3 at the end, CH2, 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 and another CH3. But the second one, it shows that 2 CH3s are branching off of that CH at the intersection there. So, in condensed form, they will be different, but ultimately they do still have the same number of the same atoms. Awesome. Constitutional is done, so let's look at stereoisomers. So, we had constitutional connectivity versus stereospatial. These isomers have the same molecular formula and the same connections. They just have different spatial positions, meaning features like going towards you or away from you, or stuck with one side up, one side down, things like that. Sketch is here to show this example. Once again, same formula for a dog here, but we're going to focus on the spatial position of his ears. Notice how they are both upwards, right? Compare that to this situation, as though he was born with one floppy ear. This is indeed a spatial difference. One would be up and one would be down. The ears are not connected any differently. They are still exactly where they are on top of his head. They are just pointing in different directions. So that would make those two scenarios stereoisomers. There is something very important to note about this spatial difference, though. They need to be effectively stuck in different directions. It can't be something you can easily change with a quick rotation. Let's take a closer look. So, these ears are spatially different due to some restricted movement. In this example, the ears are either permanently stuck upwards as pointed ears, or they are stuck with one pointed up and one floppy down. You can't just change the type of ears a dog has by simply moving them, right? If your dog has floppy ears, it has floppy ears. You'd have to surgically change that. So they are pretty much in a definitely restricted spatial position. The same applies to molecules, and I'll show you that in a moment. Just to ensure you have the right vocab to describe these features, know that when two sections are stuck in the same direction, you call it cis. When they're stuck in different directions, they're called trans. So with stereoisomers, you always have to look for cis-trans relationships, or you'll have to check for something called a chiral center, where you can have specific stereoisomers called enantiomers and diastereomers. That's a bigger topic for another video, so for now, don't worry about it. Alright, got all that? Stereoisomers have spatial differences that are restricted in movement. So let's try with a real molecule. We've got 4 carbons and 8 hydrogens, so that molecular formula is C4H8. Let me just jump right into it here. Look at these. Both do indeed have 4 carbons and 8 hydrogens. So you've got the same atoms connected in the same order. But why aren't they just considered the same molecule here? It's because of that issue I mentioned with restricted movement. Double bonds and rings can't just rotate things into place, so spatially they are not the same. View that double bond as a little lock. The one on the left is stuck with one down, one up, just like Sketch was stuck with one floppy ear, one pointed ear. Look at this scenario below. Imagine you pinch that right end and twist that bond downward. You'd get this one here. These molecules are the same. They are not stereoisomers because you can rotate them into each other's form. That works with single bonds. The double bonds cannot rotate because they are locked in place with that pi bond. So, since you cannot just switch them around, it looks like you've got one where the carbons are set in different directions, or trans, and one where the carbons are set in the same direction, or cis. Now, real quick, why didn't I include these as stereoisomers? It's because they're not. They need to be connected in the same order to be stereoisomers. But look, the one on the left has the double bond at the edge of the molecule instead of in the middle. That's a different connectivity. And the one on the right has a branched carbon instead of all of them being in line. These would be considered constitutional isomers of those that I did draw above, but not stereoisomers. Let me show you another example. Here's another scenario with restricted rotation. We've got 6 carbons, 12 hydrogens for C6H12. There are quite a few shapes you can draw for this, but here are some that can be stereoisomers. We can have a square, or cyclobutane, with 2 carbon groups coming off. I drew them both wedged, as in coming towards you, but keep in mind that's the exact same thing as if I drew them both dashed. Molecules are always moving around in space, so just imagine that rotated around and it's equal. Now let's look at this other one. It's a cyclobutane with 1 carbon group towards you on the wedge and 1 away from you on the dash. You'd have to snap that ring open to twist those carbons in a different direction, so they are restricted in movement. Once again, this is another cis-trans difference, and otherwise these atoms are all connected in the same order, so they are indeed stereoisomers. Nice! So, before some practice, let's recap what we've learned. If a molecule has the same exact number and type of atoms, but they are connected differently, those are constitutional isomers. Remember, constitutional connectivity. Next, if a molecule has the same exact number and type of atoms and the same connectivity, but different spatial positions, those are stereoisomers. Keep an eye out for things just pointing in different directions. And to add on, things pointing to the same side are cis, and those pointing to opposite sides are trans. You are likely to see this in double bonds and rings due to their restricted rotation. This doesn't apply to molecules that are simple single bonds, as those can rotate freely. Awesome, okay. So, here are a few questions to try. I'll give you a moment and we can come back for the answers. Sketch suggests you pause the video here to practice. All right, let's check it out. So, for the first one, these are indeed the same molecule. If you picked stereoisomer, remember those single bonds can rotate. They are not stuck in a trans or cis position. Look out for double bonds and rings that restrict the movement. If you said constitutional, keep in mind that these are all the same atoms connected in the same order, all in a line. No difference in structure. For the second one, here is a stereoisomer. It is as simple as drawing a transform instead of the original cis one. As long as you didn't make those methyl groups or carbon groups connected in a different order, this is the perfect solution. Finally, here are all the constitutional isomers of C6H14. Check them out. If you struggled to find them all, remember you can just keep snapping off a carbon one at a time and connecting it somewhere else, and then you'll find all the options, keeping in mind that drawing kind of mirrored forms or different rotated forms wouldn't count as a different constitutional isomer. So let me know in the comments how you did. Alrighty, that is it for now. If you want to learn more, feel free to check out some related organic chemistry topics in the playlist. And before I go, special thank you to 3 amazing students, Karima, Anthony, and Isaiah. I really appreciate the mic and it sounds amazing. I'm wishing you guys all the best. Otherwise, that is it for now. I'll catch you all later. Bye.